Hi folks, so before starting this lab, I'd like you to look at the introduction. There are some videos which I would like you to view here. And once you've done that, start looking at the procedure. Here we go, and there's the procedure. Welcome to my swamp. Today we're looking at transformers. And before we actually start looking at transformers, I just want to remind you of something we did in the last lab. If we look at this setup here, we have a DC power supply. I have a switch. It's connected to this gilly coil. This gilly coil is magnetically linked using the iron bar to the second gilly coil. And what we did in the last lab is that I got you to go like this as you change the magnetic field in the first gilly coil. We saw as the field changed, we saw that an EMF was produced in the second gilly coil, and that EMF drove a current around the circuit, and we saw the deflection of the ammeter. So when I press the button down, the magnetic field builds, it flicks to the right, goes to zero once the field is steady, and when the field collapses, it flicks to the left. Now, if you think about this, if I go like that on the switch, the needle flicks backwards and forwards constantly. If I just hold it down just for a moment, do I get power delivered? But if I go like this, I can get power constantly delivered to this second coil. Now, it would be awfully tedious to have you going like that for the entire lab. So we have a trick up our sleeves. And the trick is, if we move over here, is to use an AC power supply, because with the AC power supply, instead of you switching it off and on like that all of the time, the AC will be switching it and changing the direction of the current. Hi folks, we're going to start part A of the procedure, and part A is transformers without loads. So the secondary coil here will be connected to a voltmeter. In the setup, I have my primary coil here. This is a 400 turn coil, and this is connected to the AC power supply. We have, it's dropped a bit, we have around 4 volts on the primary power supply. And at the moment, you can see we have really nothing on the secondary. This says millivolts, so it's just a bit of noise. Why is that? Because there's no changing flux through this secondary coil. So what we want to do is to see how we can link these. These have to be magnetically linked. What we could do is just push them together, okay? And you can see as I push them together, the voltage on the secondary rose. This is a 1-to-1 transformer. Both of these are 400 turns. So I should be getting 4 volts out on here, but I'm not, because I'm leaking flux all over the place, right? They're not very well magnetically linked. So what we'll do, we'll see if we can improve on this air-to-air linkage by using this U-shaped piece of iron. It's a laminated piece of iron. We've talked for the reasons, I've explained the reasons why it's laminated in class. So if we go from this configuration where I have 4 volts on the primary, 250 millivolts on the secondary, if I now link them in this way, you can see that's a great improvement. I now have 1.63 volts on the secondary, around 4.5 volts on the primary. The primary, this is an unregulated supply, so you'll notice that the primary voltage changes depending on the load being drawn from the supply. Okay, so, but we can see that we're getting a decent fraction. What we could try is just having an iron bar linking them. This is the next part of the procedure. And again, how would that work out? And yeah, actually that's a bit better, isn't it? We've got 4.4 on the primary, 2 volts on the secondary. Of course, we know that magnetic fields like to circulate around. And so if we give the magnetic field sort of a chance to circulate around, so I can set it up on the U and then get the bar and allow the magnetic field to go around within the iron. This is going to grab it, I just know, there. And you can see that's getting pretty close to sort of the ideal voltage on the secondary. Again, it's a 1-to-1 transformer, so the voltage on the primary should be equal to the voltage on the secondary. The final configuration we're going to try is shown in figure 7 of the text. And let me quickly set up that configuration. And we basically have something like this. And here we have a lot more circuits for the magnetism to go around. I've got the two cores. I guess in the diagram's one reversed. Shouldn't make any difference, but let's stick it like that. Hey, that's pretty swanky. Hey, look, we've got 4.6 volts on the primary, 4.4 volts on the secondary. So you can see it's almost a one-to-one transformer. So it looks like that this is the best configuration that we've got. Okay, so what we want to do now is to switch the bottom one out for a 200 turn coil. So I'm going to switch this one for a 200 turn. And I need a second 200 turn coil on the top. Okay, so 200 is my primary, 200 turns on my secondary. And I connect them together. Again, this should be a one-to-one transformer. Okay, we're going to turn the voltage up. I think it says to 6 volts. And you can see, yeah, I'm getting, it's pretty close to being a one-to-one transformer. Okay, what we're going to do now is to go through the various other coils, and let's think. So now we have the configuration we had before, and we're going to look at step-up transformers. So at the moment I have a 200 turn coil on the primary, and on the secondary I have a 200 turn coil. The voltage on the primary has been set to about 6 volts, and you can see I have about 6 volts on the secondary. Okay, we know that the voltage should increase as the ratio of the turns on the primary and the secondary. So in other words, if I take off this 200 turn coil on the secondary and I put a 400 turn, that's a transformer ratio of 2, and so I should get twice the voltage out of the secondary as the primary. It's about 6 volts in the primary, so I should be getting around 12 volts out on the secondary. Again, this voltage changes a little bit because this is an unregulated supply. Okay. Okay, so I would record this data, 6.1, 11.8. Let's try the next one. The next coil I'll try is the 800 turn. So that's a transformer ratio of 4, 6 times 4, 24 volts. So I should get around 24 volts coming out with this one. 6 on the primary, and around 24 volts on the secondary. Makes sense. The next one up, 800, is 1600. So 1600 over 200 is 8. So that's a factor of 8 in the voltage. So when I connect this one, 8 times 6 is 48 volts. And you can see, again, it's very high, very close to 48 volts. Okay. The final one we can try is the 3200 turn coil. 3200 divided by 200 is 16. 6 times 16 is 96, I believe. And so when I connect this one, my prediction would be to get around 96 volts out on the secondary. And let's connect it up. And yeah, okay, that actually works really well. We've got around 96 volts out on the secondary. So you can see we've built up a simple step-up transformer. We have 6 volts AC on the primary. We're getting 94 volts out on the secondary. It's not ideal, but it's fairly close to being ideal. In the next part of the lab, we're going to sort of ask the question as to what happens when we actually put a load onto this secondary. At the moment, you appreciate that a voltmeter has a very high resistance. It's really drawing no current from the circuit. What happens when we start drawing a current from the circuit? And that will be the next part of the lab. And we're back for part B of the lab. And in this case, we have a one-to-one transformer. So we use the configuration which gave us the best flux linkage. And we have 2 400 turn coils. In this case, I've actually read the instructions, which I didn't before, and I've color coded it. We have red leads for the primary, black leads for the secondary. And so if we look at the primary side of the circuit, I have the AC power supply, and I've routed the AC power supply through the primary core, through an ammeter, and then here, this is the voltage on the primary. So these 2 meters are showing me the voltage across the primary and the current going through the primary. On this side, if I just disconnect that lead, we have the primary, that's the primary, this is a secondary. So this is the voltage on the secondary. Okay, so this is a 1-to-1 transformer, and you can see we've got 4 volts in, 3.8 volts out. So it's about 1-to-1. What we want to do now is to see the effect of loading up the transformer, that is of drawing a current out of it. At the moment, the current we're drawing is negligible because we know that voltmeters have high resistances. So here I have an ammeter. There's a lot of wires here, but the lower meter is an ammeter, the current on the secondary, and this is just a rheostat, a variable resistor. And when I connect this up, what happens? Let's take a look. I've drawn a load on it. Now, if we go back to the primary, let me disconnect it. We can just look at the primary. Connecting a load to that causes the voltage on the primary to drop. The reason is that this is an unregulated supply. So what I need to do, I need to just turn that back up so I've still got 4 volts on the primary, okay? The rheostat is connected to an ammeter, so now I can see the current being drawn on the secondary circuit by the ammeter, and I can see the voltage. The power going into the primary transformer is the product of the voltage and the current, and the power coming out is VS IS. Okay, so I know power in, power out, so I can figure out the efficiency of this. If I have nothing connected, an open circuit, then I can see that this is just totally inefficient because there's some power going in. You look at VP, IP, and nothing's coming out. I don't have anything connected. So in terms of efficiency, this has an efficiency of 0%. Now, if you think about this, if you have a cell phone charger and it's plugged into the wall, but it's nothing connected to it, the cell phone charger feels warm because it's using energy just because this is a resistance connected to a supply. This is using some energy. As a practical point, this has self-inductance, and so it has a rather high impedance across the supply. Okay, so with no load on this side, the efficiency is 0. When I connect a load, you can see that I've got some power going in and some power going out. So I can figure out the efficiency. Now what we want to do is to sort of change the load. When you're doing the lab, you have to sort of fill in a table, but I'm going to show you the effect. So here it goes. As I slide this toward me, I am decreasing the resistance. So as I decrease the resistance, you can see the current is increasing. And as I draw more load from here, I have to adjust my power supply again to maintain the 4 volts on the primary, okay? So I can get various loads onto the transformer, and in the lab, you would select various different loads, okay? To get sort of the last 2 data points, what we're going to do, we're going to remove this, and we will just use the ammeter itself. The ammeter has an internal resistance. The lights just switched out. The ammeter has an internal resistance, and we'll measure this. It's given in the table. So if I connect the ammeter directly across the transformer, and you know this isn't usually a good thing to do, right? Because the ammeter has a very low internal resistance. But connecting the ammeter across the secondary, it's putting a very low resistance on it. So you can see that we're drawing a very large current here compared to the currents we drew before. I'm going to turn the voltage on the primary back up to 4 volts. So you can see power in, power out. We're not delivering 4 volts. We've got 4 volts on the primary. We don't have 4 volts on the secondary. You can see the voltage has collapsed. If I disconnect this, let's just disconnect the ammeter for a second. Here it goes. And you can see the primary voltage shoots up and the secondary voltage shoots up. So it's almost back to 1-to-1. but you can see when I sort of put a big nasty load on the secondary, the voltage on the primary collapses basically because of the supply again. But you can see it's not behaving like a one-to-one transformer anymore. So that's one data point, and then what we'll do, we'll put 10 amps here. That's a lower resistance, I believe, and this is sort of the last data point we get. This is with the least resistance possible in it. And again, you can see that we have, in this case, let's turn that back up to 4 volts. We have 4 volts on the primary, but the poor secondary has collapsed down to 48 millivolts. It's delivering a large current, but the voltage has collapsed. And so this isn't the way you want to run a transformer. What you'll do, you'll get this data sheet and I'll give you the raw data. You have to do the calculations, but what you'll be doing is working out these efficiency values here and plotting a graph of the efficiency as a function of the current on the secondary, and also you will look at the voltage on the secondary as a function of the current on the secondary. Okay, it shows you what to plot up at the bottom. Yeah, so that's the end of the lab. Usually, yeah, I'm sort of, this is a fun lab. I'm sorry that you guys can't do it. You can see it's lots of wires all over the place and you can fiddle around with things, but hopefully this video gives you an idea of a good idea of the lab, and you'll be able to sort of read it and finish it off without too much trouble. Okay, I'll sign off now.
Boring.
Don't say boring to me.
And that concludes today's lab.